Welcome to ePG Pathshala lecture series on computer science. In this module on data analytics, let us discuss the last part of how to mine from data streams. The objectives of this module are to learn the basics of computing moments and item sets from data streams, understand the algorithms related to computing moments and item sets from data stream, and also know the basics of decaying window concepts. This lecture is organized in this fashion. First, let us understand what is calculating moments, and an overview about calculating moments will be done first, followed by estimating moments by AMS method, then counting item sets by DGIM approach, and finally we will understand in general about what is decaying window and the terminologies related to decaying window. Let us start with computing moments. Suppose you have a stream that has elements chosen from a set A which comprises of n values. Then we can calculate the moment. The moment can be in general the kth moment. So, the kth moment is defined as shown in this equation, which is summation of the number of times a particular element, say the ith element, has occurred in the given stream and to the power of k, which indicates the moment that we are trying to calculate. So, in general, what do you mean by moment? So, moment is closely related with mathematics and statistics, wherein we will be knowing in depth about the shape of the set of data points, whether it is distributed evenly or not, or in certain scenarios we will be looking in for the number of times a particular item has occurred. Sometimes it may even indicate the overall distribution of the data points. When you want to compute the overall, when you want to compute the moments, computing moments may start with the 0th moment. Keep in your mind the equation summation of mi to the power k. If suppose this is going to be 0th moment means, then k will be equal to 0. Now, if k is equal to 0, it simply is going to indicate the value. Already we know m is the number of times a particular element has occurred. So, whatever may be the value of m to the power of 0 is going to result in a value 1. So, if it is going to be summation of ones, then it indicates the number of distinct elements that has been identified so far in the given data stream. Next, let us understand what is the first moment. When we are trying to calculate the first moment, k will be equal to 1. When k is equal to 1, the number of times a particular item has occurred indicated by the notation m of I is raised to the power of 1. So, which is nothing but the total number of elements or the length of the stream. For example, if there are 3 elements in the given stream and assume these 3 elements has occurred once each. So, the number of times the first element has occurred will be 1, the number of times the second element has occurred will be 1, and the number of times the third element has occurred will also be equal to 1. If all these values are raised to the power of 1, it is going to be 1 plus 1 plus 1, which is equal to 3. So, the 3 indicates the number of distinct elements or the number of elements in the given data stream. In other words, it is also called the length of the stream. This is very easy to compute. If you are going to discuss with respect to the second moment, here the same equation k will be equal to 2, that is the number of times a particular element has occurred will be raised to the power of 2. This is actually a measure which is used for indicating how uneven the distribution is, and this uneven distribution or the second moment is also called as the surprise number S. Now, what is so important about these moments? Every moment, like the 0th moment, the first moment, the second moment, actually provides or conveys some information about the data. The zeroth moment, as already mentioned, indicates the number of distinct elements. The first moment indicates the length of the stream, and the second moment indicates the uneven distribution of the elements in the given data. So, statistically, when you want to understand the elements of a given data stream, then estimating the moments becomes very important. So, you can find moment estimation as a very important application in many scenarios. Now, let us understand what is the surprise number using an example. Assume you have a stream of length 100 and there are 11 distinct values, and all these 11 elements have occurred 10 times, that is only one of the 11 distinct values has occurred 10 times, and the rest of the 10 values have occurred 9 times each. Now, if you want to calculate the surprise number, then surprise number will be equal to 910. So, how this is computed is, this is computed based on the equation summation of mi to the power of k, where mi is the number of times a particular element has occurred raised to the power of k. Here k is the second moment since it is a surprise number. So, the number of times an element has occurred is 10 to the power of 2 plus 9 to the power of 2 and so on till the 11th value. So, put together this will be 100 plus 81 plus 81 plus 81 and so on. So, totally it will be 910. Now, let us take the same example with length 100 with the same 11 distinct values, but the number of times these distinct values have occurred changes. Only one element among these 11 distinct values has occurred 90 number of times, and the rest of the elements has occurred only one number of time. Now, if you calculate the surprise number will be equal to 8110. Now, from these two surprise number, it will be easy to say that the distribution of the elements is uniform in scenario 1 when compared to scenario 2. In other words, there is uneven distribution of the data elements in scenario 2. So, as discussed earlier, surprise number or the second moment is used for estimating the uneven distribution of the data elements in the given data stream. Let us take another example. Suppose you have a stream which has the following elements A, B, C, B and so on. The length of the stream is equal to 15, that is 15 number of elements are there. Suppose if you want to estimate the second moment of the given stream, first thing you should understand is what are the unique elements from the given stream. The unique elements from the given stream is A, B, C and D. Next, you will have to compute the number of times these distinct values have occurred. A has occurred 5 times, 1, 2, 3, 4 and 5. B has occurred 4 number of times, C has occurred 3 number of times and D has occurred another 3 times. Now, if you take these value and use in the equation of the second moment, then it will be equal to 5 square, which is the number of times A has occurred, 4 square number of times the element B has occurred, 3 square plus 3 square the number of times element C and D has occurred respectively, which is equal to 59. So, this is how second moment for given streams can be calculated. There is a generic way approach by which all moments may be calculated, and this approach is called as AMS approach. AMS stands for the authors Allen, Matthias and Szegedy. These three authors together have come up with a methodology that in general defines all moments. So, AMS method works for all moments. This actually provides an unbiased moment considering even the error. Now, how the second moment may be calculated? For every element that you are encountering, you will have to retain two information about it. One is the element itself and second one is the value. So, what is that you need to do is, you need to keep track of many variables x. So, for each variable x, we will have to store the element x dot el and the value, that is the number of times x dot val has occurred. Now, having identified the element and the number of times the element has occurred, then you will have to calculate how many number of times all these element has occurred and its summation, which is nothing but our second moment or surprise number. Now, one difficulty with respect to this method is you will have to maintain all these counts in the main memory. Only then the entire second moment or surprise number may be generated. But practically speaking, in a general stream processing model, you will always have limited main memory. Therefore, we must be very careful in addressing all elements that has been encountered so far. If we are going to analyze this AMS method, let us start with say one random variable for the beginning. Assume the stream has a length n, and at a later point of time we can increase the length to greater than n. Now, we are going to pick at a random time say t, which is less than n, and then we are going to identify the value of x. The value of x is saved in x dot val. So, the count, that is how many number of times the element x dot l has occurred, is indicated using the value c. Then the estimate of the second moment is indicated mathematically as f of x, which is equal to n into 2 multiplied by c minus 1, where c is the number of times the element has occurred and n is the length of the data stream. Now, if you are going to make use of multiple x variables like xs, x1 till xk, then the final estimate for s will be the average of all these variables estimate, which is indicated by 1 divided by k summation of function of f of x. Let us understand this example using the AMS method. Suppose the stream contains the following elements a, b, c, b till b, and assume you have 3 variables x1, x2, x3. Now, at random we are going to pick the 3rd, 8th and 13th position to define these 3 variables x1, x2 and x3. Now, when you reach the 3rd position, the element that you encounter is c. So, therefore, we set x of x dot element equal to c, and x dot value is equal to 1 because the element c has been encountered only once. So, its value is 1. Next, we are going to take a look at the 4th position. The 4th position holds a value b. So, we need not change x1 dot value. Likewise, nothing happens till position 5 or 6, but at position 7 you once again find the same element c. Now, you will have to change the x1 dot value equal to 2 because the element c has occurred twice at position 7. Now, the next position which we will have to analyze for the variable x2 is the 8th position. At the 8th position we find the element d. Therefore, x2 dot element will now have the value d and its corresponding count will be equal to 1. At position 9 and 10 we encounter element a and b. Therefore, the value of x1 value and x2 value is not affected because x1 value is related to c and x2 value is related to the element d. But at position 11 you find the element d. Therefore, which x value will be changed is, it is the x2 value that will be changed to 2 because already at position 5 the element d has been encountered. Then at position 12 we encounter an element c. Already we have encountered c 2 number of times. Since we are encountering c once again, the x1 dot value will be incremented by 1 and the new x1 dot value will be equal to 3. At position 13 we encounter a and at position 14 we encounter a. Therefore, we can set the x3 element as a and the x3 value as 1 at position 13. Next, at position 14 you encounter once again the value A, therefore x3 value will be incremented to 2. At position 15 we encounter element B, which does not affect any of the variable because x1 represents C, x2 represents D and x3 represents A. So, finally, the values for these three variables x1, x2 and x3 will be equal to 3, 2 and 2 respectively. Now, with the help of these values 3, 2 and 2, now you can calculate the surprise number using the same equation. So, which will be equal to 3 square plus 2 square plus 2 square, which is 8 plus 9, which is 17. So, the surprise number for these three variables will be equal to 17. Now, let us understand this surprise number estimate by means of expectation analysis. Assume you have a stream. Here in this diagram A, B, 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 A, B till A is the stream, and the numbers above this indicates the count, that is number of times the element has occurred. This line indicates the time axis. The second moment is going to be summation of mi to the power 2. Now, Ct is the number of times the item has occurred at a particular point of time t. Therefore, the estimate of f of x will be equal to average of n into 2 multiplied by Ct minus 1 and the summation of this particular product, which is equal to 1 by summation of n into 1 plus 3 plus 5 till 2m minus 1, where Ct is represented by means of the number of times a particular element has occurred at a specific point of time t. Here in our scenario C3 will equal to be m suffix b, where mi is the total count of an item I in the stream. Here we are going to assume this as the maximum length n. Here this n is actually the overall average, that is the group times, that is total number of times a value has been seen. 1 indicates the time and the number of times the element Ct has occurred. 3 indicates the time t when say the element I has occurred at Ct time, and this mi is the time t when the first I is seen. With this equation, let us take the inner side of this equation and then do a separate calculation. So, this series 1 plus 3 plus 5 is equal to summation of 2i minus 1, which is equal to mi square. Therefore, the expectation of f of x will be equal to 1 by n summation of n into mi to the power 2. So, we are going to replace this part of the equation using the value mi square. So, this summation of here this n and n will get cancelled. So, this expectation value will be equal to summation of mi to the power 2, which is nothing but the surprise number and the second moment. Now, when we work with respect to higher order moments, that is for estimating the kth moment, we need to work with respect to the algorithm, but we need to change the estimate. That is the same algorithm must be used, but the estimate will be changed. So, for various values of k, if you calculate the higher order moment, then for k is equal to 2, it will be n into 2 multiplied by c minus 1. If it is for k is equal to 3, it will be n into 3 c square minus 3 c plus 1, where the c is nothing but the number of times or the count of a given value. Now, when we assume k is equal to 2, we should remember that this series is going to be equal to sum of m square. So, 2c minus 1 will be equal to c square minus c minus 1 the whole square, and for k is equal to 3, the series c cube minus c minus 1 cube will be equal to 3c square minus 3c plus 1. So, in general the estimate will be equal to n multiplied by c to the power of k minus c minus 1 the whole power k. Now, when you combine all these samples together, then you will have to take the average of this group instead of considering group by group information. Once all the groups are considered, then you can even take the median of these averages. So, the average or the median of the averages may be finally considered as, say, the number of times a particular element has occurred. Now, what may be the problem? When we work with respect to stream, we discuss about the property that it is going to be infinite in nature. So, streams never end. That is, we have assumed there will be n which will be the maximum value, but in real stream this n will grow. Therefore, surprise inputs will come into picture or surprise numbers will come into picture, and hence calculating the moment becomes a difficult task. So, what may be those issues and what may be the solution? Suppose you have a variable x and n as a factor, then you can keep n separately and just hold the count of x alone. Suppose you can only store k counts, then what is that you can do is you can ignore x for a specific time and later onwards you can consider the values of x. Here the overall objective, whether scenario 1 or scenario 2, is at a starting time t, you will have to make use of a probability k by n, that is you will have to choose the probability k by n. So, what may be the solution for this is, that is when the number of elements in the stream keeps increasing, then you will have to work on the type of sampling called fixed size sampling. So, for any type of input data, ultimately you will be having a sample whose size is going to be fixed at any point of time. So, what you can do is you can choose the first k times of k variables, and for every nth element that arrives where n will be greater than k, you will have to choose it if it has a probability k divided by n, else you will have to ignore the element n, that is the nth element. Suppose if you are going to choose the nth element that arrives, then you will have to ignore any of the already existing value in x. Therefore, you will have to look in for an element which can be ignored or which may not have the property k by n, or the property will not hold good for that particular element. So, for accepting you will have to choose for a specific probability, and for rejecting an element from the existing set also you should look in for a specific probability. The second important algorithm which can be used on data stream is counting item sets. When we work with respect to item sets, the item sets are number of elements that occur often or frequently. For example, when you go to a shop and you purchase some set of items and the shopkeeper finds often 2 items are purchased together. Assume there were 10 transactions that has happened, and among the 10 transactions, 5 transactions contains a pair of item together, purchased together. The rest of the items have not occurred together, or the occurrence may be very less. Now, what the shopkeeper can do is, based on the frequency of occurrence of this item pair, the shopkeeper can place these 2 items together in the same rack, or can keep these 2 items near the point of sale counter, so that it gets notified easily or noticed easily, and the customers may be in a position to purchase that particular product. So, here you are trying to identify item pairs, and you will have to count the number of times these item pairs are occurred. So, for this a methodology called DGIM methodology is used to estimate the counts. Here, as the stream comes, say in this diagram, you will find the zeros and 1 indicating the streams. The length of the stream is say n. Now, every time you encounter a data element from the data stream as 1, it can be placed into a bucket. Now, when the new element arrives, you will have to verify whether it is 1 or 0. If it is 0, you can ignore that element, else if it is 1, then you can always place that value into the bucket. Suppose the second element is also 1, means already there is 1 in a bucket, and the second one that arrives will also be placed in a bucket. Then the third element, when you analyze, is also going to be 1. Then what happens is, you will have to identify a bucket which may be merged together, and the new one, that is the third one, can be accommodated into a new bucket. So, I am trying to merge the already existing ones, which is 2 in number. Then I will be creating a new bucket which can hold the single third one element. Now if I do this, what may happen is, as and when I encounter new ones, older ones will be merged such that the size of these buckets are always to the power of 2. So if 1 comes into picture and if I am going to hold that 1 alone as a single bucket, the size of the bucket will be 2 to the power of 0, which is 1. Suppose there are already 2 ones, then I can merge them together. Therefore, the size of the bucket will be 2 to the power of 1, which is equal to 2. Suppose if there are 4 ones, then I can merge all the 4 ones together and I can have 2 to the power of 2, which is equal to 4 ones in a single bucket. Likewise, for each and every one that I encounter, I can merge the existing buckets and create new buckets to hold the single ones which is encountered currently. This approach will result in buckets whose sizes is going to be decreasing from left to right. So when you take a look at this diagram, you will find the buckets towards the left are larger in size, but the buckets towards the right are smaller in size. Now the number over here indicates the number of ones inside the buckets. So for each and every bucket, you will be having some unique number of ones and their corresponding count. So based on this, you can identify how many items have occurred and what is the count related to those items. The extensions related to this methodology is, you can look in for frequent item pairs. So you can always have one item set per bucket and the corresponding count. But the drawback is, the number of item sets that you are considering, if it is going to be too large, then you may not be in a position to understand this. The next important topic is exponentially decaying window. Exponentially decaying window is actually a heuristic approach for selecting the likely frequent item sets. Now when you are looking in for a very popular movie and assume this popular movie is the most recently viewed one, then instead of computing the raw counts which is associated to the likes given for the popular movie, you can look in for a smooth aggregation. Now this smooth aggregation will be based on this summation equation, which is over the entire stream value. That is, when a new element A at a point of time t plus 1 arrives, then all that you need to do is, you need not go for this summation once again. Instead, you can multiply the existing aggregate information by a value 1 minus c. So this way, aggregation over say a decaying window may be considered. For counting the items, all that you need to do is, you will have to multiply, as mentioned earlier, you will have to multiply it with 1 minus c. Adding plus 1 to the count for every element means you are actually calculating a sum. This sum is going to be called as a weight for the given item x. So based on the weight, you can treat whether the given item is a frequently occurring item or not. So the sliding window that is displayed in this diagram looks like this, and the size of the window reduces in an exponential way, and the window with which you are going to look at the data also keeps reducing. So one important property of this sliding versus decaying window is, in decaying window the sum over all the weights will be equal to 1 divided by c, where c is the count which has been calculated earlier. Now example for counting items. Suppose you are working on a popular movie, then if you want to analyze whether it is popular currently or earlier, then using decaying window concept you can easily determine it. Some extensions to this decaying window concept, including item sets, is you can look in for some item sets that are currently very popular. So the problem here is, you are working on too many item sets to keep the counts in the main memory, but in reality you can always define a basket B that comes as a multiple of counts of 1 minus c. So therefore what happens is, the basket B will always contain an aggregated value to which you will always be multiplying a value 1 minus c. This actually will reduce the number of counts which is part of say given bucket. So you can intuitively have the frequently or often visited items or say products from a given web page. Another best example is you can look in for a subset of element and you can start counting the subset frequency. So, you can look in for I, j first, and at a later point of time there may be a new element added to it k, if and only if I comma j and I comma k and j comma k are all part of your original data set. How many counts do we need is, on an average you require counts which is very less than 2 divided by c multiplied by average number of times the items that is available in the given basket. Therefore, the total memory which is going to be used for counting the item sets will be very minimal. So, to summarize, estimating moments, though it is complex, it is widely used in many applications, and mining frequent item sets from a data stream leads to effective product recommendations in most of the scenarios. Thank you.